game. It's a rich thing.
What is going on, guys? Welcome back. In today's video, we're going to learn how to properly evaluate our machine learning models by using two metrics called precision and recall. So let us get right into it. Alright, now for today's video, I'm going to use a Jupyter notebook instead of the PyCharm IDE like usual. And the reason for that is that when we do something with data, when we do data visualization, when we do machine learning, I think it's just easier to work with Jupyter notebooks because we can run individual cells. We don't have to run the full block of code every time we want to do something. Visualizations are easier and so on and so forth. So I'm going to use a Jupyter notebook. However, you don't have to, so you can still follow along, do everything in PyCharm in the default Python idle. You can do it in VS Code, whatever you're using. I'm just going to use the Jupyter notebook today for this tutorial. And the topic is precision and recall. Those are two metrics that we can use to evaluate a model's performance when predicting certain things. And we're going to compare it with accuracy, and we're also going to introduce a fourth score, which is the F1 score. So this is going to happen at the end. But let's start with a very simple example. Let's say we say something like from scikit-learn datasets, we're going to import a load digits, which is going to load the MNIST dataset, which is like the Hello World dataset for machine learning. So we can say digits equals load digits, and essentially those are just handwritten digits. Let's just see what they look like. So we have data, we have target. Maybe we should look at the keys first. We have data, target, frame, and a couple of other things. We're interested in the data. Those are the pixels, and the target is then the label, so the respective digit that is displayed. So we can actually go ahead now and visualize this by saying, for that I'm going to need an import matplotlib.pyplot splt. By the way, all these libraries, you should have them. You can install them by using pip. So pip install matplotlib, pip install scikit-learn, pip install numpy, pip install pandas, and so on, if you don't have them in the command line. And what we're going to do now is we're going to say plt imshow, and we're going to show the pixels of digits.data 0, so the first one, and we're going to have to reshape this. Now the format here is not the classic 28 by 28. I think it is 28 by 28. In this case, it's 8 by 8. So we have 8 pixels times 8 pixels, 64 pixels in total. So we're going to reshape this like that, and we're going to say the color map is going to be gray. And this is a 0, for example. We can also go to something else like 20, for example, and this is also a 0. Then 25, this is going to be a 5. So we have these digits here, and we also can see that if I go and print now digits data 25.target. Oh, sorry, this was wrong. Data target 25, this is what I'm looking for. This is going to be a 5. So this is the label, those are the pixels, and this is a simple classification task, right? So you choose a model and you train a model on one part of the data to train it, and then you test it to evaluate it on another part of the data, how well it does the predictions. And with 64 pixels, this should be quite easy. So this is not the topic of today's video, how to do that. I have, I think, 2 videos on that, and this is like a Hello World example for machine learning. This is just the example that we're going to use to explain precision and recall. So let us just build a simple model to predict that. We're going to say from scikit-learn dot model selection. We're going to import the train test split, and from scikit-learn dot neighbors, we're going to import kneighbors classifier, and we're going to do not a general digit classifier, because in order to explain precision and recall, we're going to use here a binary classifier, so either yes or no. And of course, when we have 10 digits, a yes and no classifier doesn't work on all the digits. So we're going to pick one digit, for example, the 8. We want to classify if something is an 8 or not. So essentially, we can say 8 underscore CLF for 8 classifier is a kneighbors classifier. And the x values are going to be just digits.data, so the pixels. And the y data is going to be digits.target being equal to 5 as a condition. So this is going to return zeros and ones. Actually, not 5, sorry, 8. this is going to return zeros and ones. So whenever a digit is an 8, it is going to return a 1, and if it's not an 8, it's going to return a 0. So we make it a binary classifier instead of a digit classifier. So it's not going to tell us that this is a 5 or a 4 or a 6. It's just going to say yes or no, is this an 8 or not? Again, this is just the example that we use to explain precision and recall. Now we're going to split that data into xtrain, xtest, ytrain, ytest by calling the train test split xy. And let's pick a test size. Now this is going to be quite simple, so I think we're going to get close to 100% accuracy. But we're going to go with 20% test size to start with, and then we're going to just train the classifier. So ATLF dot fit on xtrain and on ytrain. Now, what is important here is that when we now say, for example, let's evaluate this classifier, ACLF.score, xtest, ytest, this is going to give us a score. In this case, 98.888%. So pretty high score. But what you need to understand about the score is that this is accuracy. So accuracy is defined as how many samples did I look at and how many of them did I get correctly. So we can calculate the score ourselves by just saying, okay, give me the predictions. So manually, we're going to say y predictions is the 8 classifier dot predict. So based on the training data here, we predict now the test data, which is the same as scoring, but we're going to do the comparison manually to understand what is happening. And we can now say correct basically means that we get the sum of the correct classification of the correct classifications. Oh, sorry, this is one step ahead. What we want to do to get the correct classifications is we want to compare the y predictions to the actual y test data. So this again is going to give us zeros and ones, a 1 every time when those two are the same, and a 0 every time they're not. So we can get the accuracy by saying sum of correct, so sum all the ones divided by the length of correct, by basically everything. So this gives us the percentage, and now I can just go ahead and print the accuracy. There you go. So this takes all the samples, all the instances, how many of those did we get correctly as a percentage. This is the accuracy. And accuracy is actually quite a good metric to look at. However, sometimes it's going to be not enough, and sometimes it's going to be misleading. And oftentimes we also want to have more detailed information about the model's performance. Let me show you a simple example here. Let's go ahead and say now the y values, the y predictions are not going to be based now on the 8 classifier that we trained. We're just always going to say that whatever we see, it's not an 8. So we're going to produce a prediction set of only zeros. We're going to say y always underscore no is going to be 0. So basically no for length of x test. So for each sample that we see while testing, we're going to say this is not an 8, this is not an 8, this is not an 8, and so on. And then we can go ahead and basically say the correct classifications are going to be y always no being equal to y test. And the accuracy is going to be the sum of the correct classifications using that strategy divided by the length of the predictions. And then we can just print the accuracy. And what you see here is that we get 89.72% accuracy. 89.72% of the time we do the correct classification, even though our prediction set looks like that. Only zeros. Always saying no, no matter what we see. Which means that whenever we see an 8, our classification is wrong. We basically always, whenever we see an 8, we say no, no, no. But every time it's not an 8, and this is way more common, we have 0, 1, 2, 3, 4, 5, 6, 7, 9. All these cases, we make the correct classification. So we have a stupid classifier, but it works, it has a high accuracy. However, this is not a good model because every time we see an 8, we don't recognize it. It doesn't recognize 8s at all. It doesn't have any intelligent. And because of that, we can use precision and recall to actually determine more specific metrics. Because the recall, for example, is a metric that tells you, okay, from the, whenever you see a correct sample, in this case an 8, an actual hit, how many times or how much percent of the times you see an 8 do you actually recognize it as an 8? This is the recall. In this case, it would be 0%, because we see a couple of 8s, and 0 times we say, yes, I recognize an 8. The recall is 0. The recall is very bad, very low. Precision, on the other hand, says, when you say something is an 8, how many times are you actually right? So how many times when you say something is an 8, is this actually an 8? And we're gonna do that here first of all by just importing, or actually let's do it from scratch first. And for that we're going to need a confusion matrix. So the confusion matrix essentially is telling you your misclassification. So we're gonna say from scikit-learn.metrics, we're gonna import the confusion matrix. And then we're gonna say confusion equals confusion matrix of, and we're gonna use the k-neighbors results here. So x, what was it, y-pret and y-test. And now we can print that, and you can see what this looks like. Confusion matrix, no, actually not the confusion matrix, the confusion, there you go. And in this case, let me just look this up here because I always forget how this is structured. Now, the right column, so 2 and 35, means we predicted yes. So right is when we say something is an 8. Left is when we say it's not an 8. And the top row means that it is not an 8. And the bottom row means it is an 8. So basically, this means that here we have the correct classifications where we said 35 times we said that it is an 8 and it was actually an 8. 2 times we said it is an 8 but it wasn't an 8. 2 times we said it is not an 8 but it was an 8. And 321 times we said it's not an 8 but it wasn't, and it also wasn't an 8. So those two numbers here are correct, and those are the misclassifications, either true false positives or false negatives. And based on those things now, we can actually go ahead and compute precision and recall. So as I said, the precision is essentially when we say something is an 8, how often is it actually an 8? And because of that, we're going to pick this value here. So those are the correct true classifications. So when we say it's an 8 and it is also an 8, 35 times. So confusion 1, 1, because we go into the second and second, 1, 1. Confusion and then divided by, so the amount of true positives divided by the amount of true positives and false positives. So confusion 1, 1, and the false positives are 0, 1 here. There you go. And this is now the precision. So we can go ahead and say the precision, in this case, 94.59%, which means that when we say something is an 8, 94.59% of the time we are right. This is the precision. The recall is now what we also said, when something is actually an 8. So when we see an actual 8 in front of us, when the model sees an actual 8 in front of it, how often does it actually recognize it? So how often does it not miss an 8, you could also say. And for that, we take again the true positives. So how often it recognized a correct 8 divided by, also again, how often it recognized it correctly, and how often it was shown without to be recognized. So 1, 0, which is this here. And I think in this model here, the precision and recall are the same because we have 2 and 2. There you go. But it doesn't have to be like that. This is just in this case because here we have a 2 and here we have a 2, and we take this plus this and this plus this, and this is the same result. But it doesn't have to be the case. And let me show you how this looks here when we have the always no predictions that we talked about. So I can say here confusion equals confusion matrix. And we're going to say here now y always no and y test. So our primitive strategy in a confusion matrix looks like that. We never say that this is an 8. So the whole bottom list here is empty because we never say yes. And because of that, we can never make the mistake of saying yes while it's not true. but we also never say yes when it is true. And because of that, if I now go ahead, and for this we're now not going to do it like that, we're going to import the respective scikit-learn modules. We're going to say from scikit-learn.metrics, we're going to import the precision score and the recall score, like that. And we're now going to say precision equals, and the function is, let me just see where I had it. The function is precision score, and first we enter the y test, so the correct values, and second we enter the always no values. And in this case it doesn't work. Why? Because the precision cannot work if we don't have a single classification, so in this case it doesn't work. However, if I now say recall, this is going to work. Recall score, y test, y always no. And the recall is 0. 0% of the time when we see an 8, we actually recognize it. So this is pretty bad. If we look at the accuracy, we don't get that picture. 89.7% is not too bad. It's not perfect, it's not very good, but it's not bad. But when we look at a recall of 0, this is horrible. This is a very, very bad model. Now we can also try the opposite. We can try to say always yes. So essentially y always yes is going to be once times the length of not this x test. There you go. And then we're going to get a different confusion matrix. So if I now say confusion equals confusion matrix of y always yes and y test, then we're going to see that the first row is empty. So we always say it is an 8. Because of that, guess what? The recall is going to be phenomenal because we recognize every single 8. If I now say recall score of y always yes and y test, this is not true. Oh yeah, I messed up the order. We need to do it the other way around. So first y test and then y always yes. And then you can see we have a recall of 100%. Obviously, because whenever we see an 8, we say it is an 8. So we never miss a single 8. But we do so for every number, which means that in turn, if we now look at the precision score of y test and y always yes, this is going to be horrible. 10%, 10.27%, because basically whatever we see, we say it's an 8. And obviously it is not, because we have a lot of other digits, and because of that the precision is very low and the recall is very high, and the accuracy is going to be pretty bad here in this case. Even though it's not the case for always no, but the accuracy is going to be quite bad for this, because we basically do a lot of misclassifications in this case. So one last thing that we want to introduce here, which makes sense to introduce here, is the so-called F1 score. And the F1 score is the harmonic mean of precision and recall. And harmonic mean basically means that smaller values are affecting the final result more, which in turn means that in order to have a high F1 value, we need to have a high recall and a high precision. We cannot achieve a high F1 score if one of the two values is very low. So we have to have both quite high in order to reach a high F1 value. And the formula is essentially just F1 equals 2 divided by, and then 1 divided by precision plus 1 divided by recall, like that. And for that, we're going to say, oh, sorry. Now I messed this up again. Come on. Y always yes. There you go. Recall is that. And precision is that. And the F1 score is going to be that. And in this case, the F1 score is very low because the precision is very low. If we have a high precision and a low recall, it's also going to be very low. If both are decent, we're going to have a decent F1 score. So actually, we can do the same thing now for the actual values of the k-neighbors classifier. So recall score for Y test compared to Y predictions, and precision, same thing. Like that. And then what we can also do here, we can import the F1 score from scikit-learn. So from scikit-learn.metrics, import F1 score. And now we can just say print F1 score of. Oh, actually, we don't need that. I forgot that. We don't need that. We can do it directly like this. It's going to do everything behind the scenes. So Y test, but I think it can actually be useful. Can I somehow get this back? No, okay. But when we now go and say Y test and Y predictions, we get a high F1 score because the precision and the recall are pretty high. We can see them here. Both are high, and in this case, both are the same. And because of that, we get the same F1 score as well. But we can change things up a little bit. We can make it harder by increasing the test size, meaning that we're going to train, in this case, now on 30% of the data to predict 70% of the data, which is way harder. And if we do it like that, let's run all of this here. We get a lower score, but we should probably get different precision and recall. There you go. Oh, no, it's the same. Let's go with a different digit, maybe. Let's go with a 5. So let's just run this from the beginning again. Let's just force different results. Okay, here we have a pretty high F1 score. And we have, again, the same recall and the same precision. So let me just see real quick here. No, I'm looking at the wrong values. What am I doing, mate? But still, we have a different precision and recall. So let's change this one more time to 90% and see if we end up with different values here. There you go. Now we have a different precision and recall. So we have a precision of 91%, which means that when we say it's a 5, in 91% of the cases it is a 5. And when we see a 5, 96% of the time we recognize that it's a 5. So they're different, but they're both quite good. So we can actually go ahead and we can see that the F1 score is 94%. The F1 score is still very bad for the always yes, always no strategy, because of course either recall or precision is going to be very, very low. And because of that, the F1 score is also going to be very low. This is the idea of the harmonic mean as opposed to the normal mean. The normal mean just takes the mean, and the harmonic mean gives more relevance or more weight to small values. So if one value is small, this is going to influence the F1 value a lot, even if the other one is quite high. So that's it for today's video. I hope you enjoyed. I hope you learned something. If so, let me know by hitting a like button and leaving a comment in the comment section down below. And of course, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching. See you in the next video, and